So we were looking at this problem in the last class, and we said that the problem states a piston cylinder device contains 0.85 kg of refrigerant R134A. So the fluid has been specified for you to be R134A, and initially the fluid is at minus 10 degrees. So this fluid is at minus 10 degrees initially. The piston is free to move, has a mass of 12 kg, diameter of 25 centimeter. The local atmospheric pressure is 88 kilopascal. Heat is transferred to the refrigerant until the temperature is achieved to be 15 degrees. The first thing you have to do is to determine the final pressure. We said that this is state 1. If this is your state 1 where your refrigerant is at minus 10 degrees centigrade, some heat is being added to your system and your system reaches to a new state where the temperature is 15 degrees centigrade and you have to determine the pressure in the cylinder. This is schematic. And we discussed that the pressure inside the chamber should be equivalent to the external pressure acting on the refrigerant. So the pressure inside, P inside, which is acting upwards, should be equivalent to whatever is acting downwards, and the pressure acting downwards is nothing but essentially P atmospheric plus the pressure due to the mass of the piston head, which is mg divided by the cross-sectional area on which it is acting. Since in state 1 and state 2, this is not changing. The atmospheric pressure is not changing, the weight of the piston head is not changing, so the pressure at state 1, outside pressure at state 1 is equivalent to outside pressure at state 2. Therefore, the inside pressure at the two states would be the same. We have discussed it so far. Is it clear so far?
Yes, sir.
All right. So we say that pressure P2 is equal to P1, atmospheric pressure plus the pressure due to the weight of the piston head, and we say this is equivalent to, this is atmospheric pressure, mass of the piston head, acceleration due to gravity converting it into weight, the cross-sectional area on which this is acting, and this 1000 converts the pressure into kilopascal, so you have 90.4 kilopascal pressure acting in both the states. Now you have two properties available for both the states. For state 1, if I say state 1, for state 1 my temperature is minus 10 degrees centigrade, my pressure is 90.4 kilopascal. For state 2, my temperature is 15 degrees centigrade and the pressure is 90.4 kilopascal. The first part is done. The second part is the change in the volume of the cylinder, which is associated with the specific volume at state 1 and specific volume at state 2, and the change in the enthalpy of the refrigerant, which is again associated with enthalpy at state 1 and enthalpy at state 2. Now these are the properties that you normally extract from the tables. But in this case, you have to identify the table first, that which is the relevant table from where you can extract the data. So you have to find out the table first. In order to do so, you will first switch towards the saturated refrigerant pressure table. Like you had saturated vapor temperature table and pressure table, you have saturated refrigerant, the pressure and temperature table. So you will go to saturated refrigerant pressure table. This is the table. If you see, your pressure is 90.4 kilopascal. Your pressure is 90.4 kilopascal. And if you see, this pressure lies between 90 and 100 degrees. So you have to interpolate for 90.4 kilopascal in order to determine the saturation temperature. Why you need the saturation temperature, I'll come to it in a minute's time. But the first thing you have to do is to find out the saturation temperature for this pressure, which lies in between 90 and 100. So I have constructed this table where 90.4 kilopascal is the one for which temperature is to be found. The immediately lesser value is 90 kilopascal, for which temperature is minus 28.65, and the immediately higher value is 100 kilopascal, for which temperature is minus 26.37 degrees centigrade. Once we do the interpolation, we find out the value of temperature to be minus 28.65. So for 90.4 kilopascal, this temperature is the saturation temperature. All right. Now, if this is the saturation temperature, let's say this is temperature specific volume plot for the refrigerant R134A, and let me draw the constant pressure line, which is 90.4 kilopascal line. Let me draw this line, which is, this is the 90.4 kilopascal line. Now, for 90.4 kilopascal line, what is this temperature?
Minus 28.56.
Very good. So this is minus, just a minute. So this temperature is minus 28.56, which is the saturation temperature. This is minus 28.56. Now, for my state 1, what is the temperature?
Minus 10.
Minus 10 degrees centigrade. Is this temperature above this line or below this line?
Below. Above,
Above.
sir. Above. Minus 10. Above.
All right, it is above. And for the state 2, my temperature is what? 15 degrees centigrade. Is this temperature above this line or below this line?
Above this line, sir.
So both the temperatures fall in which region?
Superheated vapor region.
Very good. So 1 and 2 lie in superheated refrigerant, in the region where you have superheated refrigerant. Vapor is normally associated with water when you're dealing with water. The superheated refrigerant region. That means you have to go to the tables of superheated region. So far, is it clear?
Yes, sir.
Yes.
All right. So this is what we have concluded so far, that the saturation temperature at 90.4 kilopascal is essentially minus 28.56. Since both the temperatures are above the saturation temperature, you'll be in the superheated region, not the vapor region. Since you're talking about refrigerant, you'll be in the superheated region. Vapor is normally associated with steam tables. So if you go to the superheated table, superheated refrigerant R134A, this is the table, superheated refrigerant R134A, you would see that the pressure given is 0.06 megapascal, and then the table is given for 0.1 megapascal. Your temperature is 0.904 megapascal. This comes, sorry, 0.09 megapascal. So 0.09 comes somewhere in between 0.1 and 0.06 megapascal. This is in between these two values, and the table for this is not given to you. 0.04 megapascal. Table for 0.09 is not given. So you will have to find the interpolated values for this pressure. Your first case is easy where you have temperature equals to minus 10 degrees centigrade. So you have the value of 0.06. You for 0.06 minus 10 values are given to you. This column is given to you for both the pressures. So you'll construct a table. You need the value of specific volume and enthalpy. So you'll construct a table for minus 10 degrees centigrade, sorry, for minus 10 degrees centigrade, 0.06 megapascal specific volume and enthalpy are given to you. For zero point 0.1 megapascal, they are given for you. 0.094 megapascal you will find out using the interpolation. So first you will use at minus 10 degrees centigrade. First you will use this table to interpolate and find the value for 0.09 megapascal, and then you will use the enthalpy table along with the pressure table to find out the value of enthalpy, interpolated value of enthalpy for 0.09 megapascal and minus 10 degrees centigrade. These are the interpolations that you have done for enthalpy and specific volume. And once you do that, you will find out that your uh, specific volume at state 1, here your pressure is 0.09 megapascal, temperature is minus 10 degrees centigrade, and your enthalpy value at the same pressure and temperature is found out using the interpolation. Clear enough so far?
Yes, sir.
Now, the second thing is you have to find out for the second temperature. If you remember, the second temperature for the second temperature for your state is 15 degrees centigrade, and the pressure again is 0.09 megapascal or 0.0904 megapascal, which again lies in between. So now not nor the pressure, neither the temperature 15 degrees. The data for that is given to you. In this case, you'll have to do double interpolation. One is the interpolation for the pressure, since the pressure lies in between the given data, and the other is the interpolation for the temperature because 15 lies in between 10 and 20. So I'll start with the easier one. I'll first find out the specific volume and enthalpy at 0.06 megapascal for 15 degrees centigrade. Similarly, at 0.10 megapascal for 15 degrees centigrade. Once I have the values for these two pressures at 15 degrees centigrade, then I'll interpolate for 0.09 megapascal. So the first thing I specified that I'll do the interpolation for 0.06 megapascal and find out the values at 15 degrees centigrade by using the value of 10 and 20 degrees centigrade. So I'll find V and enthalpy for 15 degrees centigrade at 0.06 megapascal. Similarly, I'll do the interpolation at 0.10 megapascal and find out the values for 15 degrees centigrade by interpolating between 10 and 20 degrees centigrade for specific volume and for enthalpy. Once I have found out the values, these are the values which are plugged in. So this table would help me fill in this column, these two columns, and this table would help me fill in these two values. Now for 0.094 megapascal at 15 degrees centigrade, I can interpolate for specific volume and enthalpy between these two pressures. Once I interpolate, I'll have the values at state 2, 15 degrees centigrade and 0.094 megapascal. This is the specific volume and this is my enthalpy. Once I've done that, I'll have these two tables with me. The first table is for state 1. State 1 is this row, minus 10 degrees centigrade, 0.094 megapascal. This is the specific volume. This is my enthalpy. State 2, 15 degrees centigrade, 0.094 megapascal. This is the specific volume and this is the enthalpy. Once I have found out these values for specific volume and enthalpy, the change in specific volume would be just the difference between the two states, state 2 minus state 1, the specific volumes, and if I multiply it by the mass is given, I'll come to have the total change in volume. Similarly, if I have the change in enthalpy, difference between state 2 and state 1, I'll multiply it with the mass, which is 0.85 kg, and this would give me the change in enthalpy. Clear enough?
Yes, sir.
Excuse me, sir. Excuse me,
Hmm.
sir. Can we
Please.
find the change in volume by ideal case equation?
Ideal gas equation?
Sir, we have been given, sir, pressure, volume is missing, or temperature is also given, R is constant.
R134A is a refrigerant which is liquid. Alright?
Okay, sir. Sir, but at the given temperature, it lies in the superheated region.
Yes, it lies in the superheated region, but for that R134A, if you remember, for the superheated region we saw for water, the if I have the slides, let me go back. Yes, if you remember this slide, for superheated region, you have calculated the error. You have calculated the error from the data given in table and the ideal gas equation. And for the error which is less than 1%, you can apply ideal gas equation. So this is already done for water vapors. But in case of refrigerant, you don't know what is the error that you will be having for a specific pressure. If your pressure is 0.904 uh, megapascal or 90.4 kilopascal, what is the error that you'll have using the ideal gas equation and uh, the tables. If water is having error of 1% and 10 kilopascal, I suppose 90.4 kilopascal is not a good enough pressure to use. All right. So we have looked into the numericals by utilizing the table. The important thing now is how can we solve the same problems uh, if we have to solve them on WES software. So I'll now go through the examples, the same examples that we have solved so far, and try to solve them for you on WES software so that you become familiar with the software also. So a rigid tank contains saturated liquid water at 90 degrees, determine the pressure and the volume in the tank. So this is the state that you're talking about. You've already seen the example. At this point, your temperature is 90 degrees centigrade and your X value is 0. For solving on WES software, you need to have two unique properties for the state of system. To find out the rest of the properties of a system, you need to have two unique properties. So temperature is given to be 90 degrees centigrade and X value is 0. You know that X is 0 over here and X is 1 at this point. Anyways, so for this condition, temperature is given to be 90 degrees, X is 0. You have to find the pressure and the volume in the tank. You use the table A4 to find out the values normally. I'll not go into that. I'll directly go to the WES software. In the WES software, this is the script that I have used. I'll explain you how do you use this script. Now, in WES software, if you want to store the data in a tabular form, what you have to do is that you have to first define the variable. For example, I'm using T for temperature. So the software would generate a column for temperature T and I'll specify the row in which I have to store the value. So I'll specify 1. This means for column T, row 1, store the value of 90 degrees centigrade. So the WES software would recognize this column as T, this row as 1, and store the value of 90 degrees for me. If I write T2, So it will go to another row and store the value of whatever I write over here. Let's say 40, so it'll store the value of 40 over here. Anyways, T square bracket 1 equals to 90 degrees means for column T row 1 store the value of 90 degrees centigrade for me. If I'm writing mass and I don't want to store it in the table, I'll just write mass equals to 50 kgs. So I have not stored this value in the table. Now temperature is given to me, mass I have written. I want to find out, the first thing I want to find out is the pressure, and I want to store it in the table. So I say use another variable P and store the value in first row of the column P. What is the value? Value is being found out using the table, and use the inbuilt function of pressure. So the WS software would now be using the inbuilt function of pressure which is there within the software. Whenever I use this function pressure, it means the software has to find out the pressure. From where do the software would find out the pressure? I have to specify the details in the brackets. There are three details I have to specify. If I'm asking for pressure, I have to specify the table. Since we are talking about water, I'll specify steam underscore IAPWS. So you have to use steam tables or the water tables to find out pressure. And how would you find out pressure? I have to specify two properties. One property I'm specifying is temperature. T equals to the value stored in the table T1 over here. So T equals to T1. And the second value I'm saying is X equals to 0 because I'm talking about saturated liquid. Similarly, I asked the software to find out the value of a specific volume and store it in the column having small v and row 1. How would the software find out the value? You'll use the inbuilt function of volume. When you'll use the inbuilt function of volume, the software would automatically find out the specific volume. From where would the software find out the specific volume? You will write down steam underscore IAPWS. That means use the steam tables, and two values that you have to use or two properties that you have to specify again is the T temperature value stored in column T row 1 and X value is equals to 0. So the pressure would be found out, specific volume would be found out. If I want to calculate the mass or the volume of my system, volume is equals to the value stored in column V row 1 multiplied by the mass that I have specified over here. Now if I run this program, now, I'll have these two windows open. This is the equation window where I have written equations. So this is the equation window where I have written the equations. This is the table that I generated. I specified three variables, T, P, and specific volume, and I only specified one row with each of the column. So temperature is something that I specified myself. Pressure is what is found out by the software and stored in value in the row 1. Similarly, specific volume is the volume which is being found by the software and stored it in the volume. Since I don't specify any column with it or I don't specify any row with it, I'll have the volume in the solution window. So I'll have the value of volume in the solution window. Is it clear? Moving on, the second aspect of software, we looked into another case where the saturated vapor is given to you, pressure is given to you, volume is given to you, and you have to find out the temperature and you have to find out the mass of your system. So I have used this script where I have stored the value of pressure. So I have used the column B, row 1, I have stored the value of pressure to be 350 kilopascal. Volume I have just specified as 0.06. I have not stored in the table. To find out the temperature and store the value in column T, row 1, I have used the function temperature, steam tables. The two properties given is the value of pressure stored in column P row 1, and the x value is given to be x is equals to 1 since you're talking about saturated vapor. Similarly, specific volume is found out and stored in row 1, and and the software has been asked to find out the volume using steam tables. Pressure to be used is stored in column P row 1, x value is 1. And how do you find out the mass? Mass is simply the volume divided by the value stored in column V row 1. Once you run this program, you will see that this is the pressure that you gave. This is stored in row 1. Temperature is found out by the software as per this eh, this command, and specific volume has been found out and stored over here as per this command. And this is the mass that has been calculated by the software using the command of volume divided by the value stored in column V row 1, which is your specific volume. Moving on, you had another example in which it was said that the saturated liquid water is completely vaporized at 100 kilopascal. So you knew that your pressure is 100 kilopascal. Your state 1 is x equals to 0. Your state 2 is x equals to 1. You have to determine the volume change and the amount of energy transferred to water. In order to do so, this is the solution that we did from the tables. In order to do so, we have written this program. We say that the mass is 0.2 kg. We have specified two rows now, one for state 1, the other for state 2. So the column P row 1 specifies the state 1 pressure, which is 100 kilopascal. Column P row 2 specifies the pressure for second state, which is 100 kilopascal. Specific volume stored in column B row 1 for the state where your pressure of state 1 and x is equals to 0, that is saturated liquid. Similarly, specific volume stored in row 2, you'll use a function of volume, pressure equals to P1 stored in V1, and x equals to 1 for saturated vapor. Similarly, you'll find out H equals another column for enthalpy, which is defined by H stored in row 1. Use the function of enthalpy. Where to find out the enthalpy from? Steam table. Two properties: pressure stored x equals to 0 for saturated liquid, H equals to 2, enthalpy, steam tables, pressure equals to 1, x equals to pressure stored in row 1, and x equals to 1 for saturated vapor. Once you have these values, the software would find out the VFG as the difference of specific volume stored in row 2 minus specific volume stored in row 1. Similarly, HFG value, the enthalpy value stored in row 2 minus enthalpy value stored in row 1. V change and H change is simply these values multiplied by the mass. Once you run the software, you'll have now two rows, one for state 1, one for state 2. This is saturated liquid, this is saturated vapor state. Specific volumes and enthalpies are being calculated by the software. These are the values V and HFG. Since you have not stored them in the table, you'll find the value in the solution window, VFG and HFG. And once they are multiplied by the mass, which is defined by M, these two, you'll have H change and V change value in the solution window. Moving on, we had this example where G.
मैं स्क्रीन करो प्रीवियस एग्जांपल में हमने वॉल्यूम एडिट की, लेकिन हमने तो चेंज वॉल्यूम करना था, सब्ट्रैक्ट नहीं करना।
जी सॉरी
सर, ये वॉल्यूम हमने ऐड की है,
वॉल्यूम ऐड किए हमने, कहाँ पे ऐड किए?
V1 प्लस V2।
एक मिनट जी, बताइए कहाँ पे ऐड किए?
सर, ये V1 प्लस V2 की हमने
इस इक्वेशन में।
जी सर,
इसमें V2 माइनस V1 है, प्लस कहाँ पे? So the next example was that of a rigid tank which contains 10 kg of water at 90 degrees C. The water is you have to determine the tank. This is the example. X is what X is to for this state you have to determine the pressure in the tank and the volume of the tank. So the total mass is defined by the variable m. So m defines the total mass for state 1, which is rho 1 stored in 10 kg. Mass of liquid is 8 kgs, mass of vapor is 2 kgs. You have not stored these values in the table. You've just defined these constants, mass of liquid, mass of vapor. T is stored in table, T column, row 1, the temperature is 90 degrees centigrade. X is stored in table, X is defined as X variable row 1. And what is it? It is the constant which is being defined as mass of vapor divided by the total mass stored in row 1 m. So this essentially is 2 divided by 10, which is 0.2. So the value of 0.2 is stored for x in column x row 1. You have to determine the pressure. So pressure is stored in column P row 1. How do you find out? You use the term pressure, steam table, specify one property as temperature, which is stored in column P row 1, and another property as x, which is stored in column x row 1. You have already stored that value. Similarly, for specific volume, use the volume function. Steam IPA WS state. When you have to find out the volume, you just multiply the specific volume stored in column V row 1 multiplied by the total mass stored in column M row 1. If you run this program, you have several variables Vi, the specific volume, pressure, temperature. These two values are found out by the software. These values were plugged in by you, and xi is something which was calculated based on the mass of vapor and this mass. And the volume is something which is not stored in the table, and you can find out the volume value in the solution window. I hope it is clear to you. Moving on, this was the example you had been given with pressure and the temperature of the water. If you identify the region, do the interpolation. You first found out the table to be superheated table. So your region was superheated, and then you did the interpolation to find out the temperature. Now, when you are doing with the software, I'll show you how and this would be done. So the first thing is you will specify your pressure, which is stored in column P row 1. The second thing is your enthalpy stored in column H row 1. The next thing is you ask the software to calculate the temperature. So you'll use the temperature function, steam IAP AWS table, two properties, pressure equals to P stored value of P in stored value of pressure in column P row 1 and stored value of enthalpy in column H row 1. This is it. Up till these three lines would calculate the temperature of water for you. I have used additional line to find out the value of X, which is quality. So I have stored that value in column X row 1, and I've used the function use quality, find out the quality from steam tables, use pressure value and enthalpy value stored in the respective columns. Why I've used that, I'll explain in a minute's time. So if you've written the first three lines, you will find out your temperature to be 216.1. You don't have to find out whether you are in compressed liquid region, superheated, or mixed region, and you don't have to do the interpolation also. The software will do it for you. X value stored, the quality value stored in X1 comes out to be 100. Now, you know that the X value varies between 0 and 1, 0 for saturated liquid and X1 for saturated vapor. In the software, when you see X equals to 100, it means you are talking about superheated vapor region. And if X value is minus 100, it means you are in the compressed liquid region. So I've I have calculated this value just to show that the software says that your system is in superheated vapor region. All right. Moving on. This was the example where you had to calculate the internal energy of a compressed liquid at 80 degrees centigrade, 5 megapascal of pressure from the compressed liquid table, and the approximation using the saturated liquid data. Saturated liquid data approximation was what? Internal energy is approximately equal to the saturated liquid value at the desired temperature, 80 degrees centigrade, or the given temperature. This is the approximation that you used. Anyways, you've already done this. Again, for the saturated liquid data, you have to do the interpolation. In terms of WA software, you just have to specify the pressure, P1 stored 500 kilopascal, temperature, T1 80 degrees centigrade. For the compressed liquid table, you will use the exact value. So U stored in 1. Int energy is the function used for internal energy. So int energy is the default function used to find out the value of internal energy in the WA software. Steam table, pressure and temperature given. This whole combination is given to find out the exact value from the compressed liquid table. U approximate is another column. This is another column defined for U. In the first row, you will store the value of int energy, again using the steam table. Temperature is same, that is 85 degrees centigrade. And instead of using the pressure, you will use the saturated liquid value where x equals to 0. So this is the approximated value for the saturated liquid data. Clear enough?
Yes, sir.
All right. Moving on. We are left with one more example. This is the example that we did today. In this example, we knew that our pressure equals to P1, P2 equals to 90.4 kilopascal centigrade and T2 equals to 15 degrees centigrade. This is given to me. So for each of the states, state 1 and state 2, two properties are known to me, and I have to find V1, V2, H1, and H2. These are the properties I need to find out. So I'll write the program again. 2 rows for 2 states. Mass is 0.85 kg. Pressure for state 1 stored in row 1 is 90.4. Pressure for state 2 stored in row 2 is 90.4. Temperature for state 1 minus 10 degrees centigrade. For state 2 stored in row 2 is 15 degrees centigrade. These are the properties which we have found out for state 1. Number 1 is the specific volume. Use the function of volume. Use R134A. Now you will not use steam IAPWS. You will use R134A tables. So the software recognizes R134A as the refrigerant table. You'll use P equals to P1 and T equals to T1 for state 1. Similarly, in enthalpy, you'll use the function of enthalpy, R134A table, and the properties of state 1. Similarly, for quality, you'll use the function of quality, R134A, P equals to P1 and T equals to T1. You'll do the same for state 2, but you'll store the values in row 2. Find out the volume, enthalpy, and quality for the properties at state 2. P equals to P2, T equals to the value stored for the state 2. Volume change is the difference in the specific volumes of the two states stored in row 2 minus row 1 multiplied by the mass, which is defined by M. And H change is the enthalpy change values, H2 minus H1 multiplied by the mass. H2 is the value of enthalpy stored in row 2. H1 is the entire value of enthalpy stored in row 1 for state 1. Once you run the program, you'll have the values of, these are the values that you plugged in for the two states. This is state 1, this is state 2, this row. H, V, and X, basically they are calculated. This is being calculated for row 1 and this is being calculated for row 2. And once they are calculated, you use the last two lines, the volume change and H change. They are not stored in the table since you have not specified the row with them. These are shown in the solution window. And if you see 100 and 100x value again means that you are in the superheated region for the refrigerant. Clear enough? All right. So I'll stop over here.